Welcome to the deep dive. We interact with the physical world constantly, but increasingly we're doing it through a digital pane of glass.
Hmm.
You wake up, you tap a screen, and a machine downstairs grinds coffee beans.
Right, yeah.
Or you approach a laboratory airlock, a proximity sensor registers your presence, and heavy mechanical servos disengage the seals.
It's everywhere.
It really is, whether it's an industrial manufacturing floor, a hospital ICU, or even just, a simple smart home setup.
Yeah.
There are countless physical devices.
Hmm.
Valves, relays, flow meters, heart monitors.
All of them constantly translating physical reality into digital data.
Exactly. It's this relentless, high-stakes conversation
Yeah.
between the analog world of electrical voltages and the digital realm of code. But we rarely think about the actual infrastructure of that translation.
Yeah, the assumption for most people is usually that this translation is just an inherent property of modern technology.
Like it just happens by magic.
Right, exactly. You plug a sensor into a computer and the data simply appears on a dashboard. But the reality is that the boundary between hardware and software is, it's fraught.
Fraught with latency.
Latency, bottlenecks, and incredibly bloated middleware. Getting a physical voltage to manifest as a pixel on a web browser in true real time is a notoriously complex engineering challenge.
Which is the core of our exploration today. We're looking at a single, incredibly detailed architectural blueprint titled Forging the Compass.
Yeah, this is a great one.
It comes from William L. Weaver, an engineer pulling from 30 years of STEM experience, specifically working within the Sensors and Advanced Instrumentation Laboratory, or SAIL.
30 years. I mean, when someone has spent 3 decades in advanced instrumentation, they've lived through every paradigm shift in hardware to software communication.
Oh, absolutely.
And they've also lived through every failed trend.
Fair point.
No, really. 30 years in a laboratory setting means dealing with the transition from massive proprietary SCADA systems running on isolated mainframes to the modern era of the Internet of Things, where everything is expected to be accessible via a web browser.
Right.
Weaver has seen the accumulation of software layers that characterize modern development, and his current work is a direct reaction to that accumulation.
And his reaction is encapsulated in the acronym COMPASS. That's Coherent Orchestration of Microcontroller, Python, and Sensor Systems.
It's a mouthful, but it's precise.
It is. And our objective today is to unpack this blueprint. We're going to dismantle it and look at the underlying philosophy for you, the listener. Because Compass isn't just a tech stack.
No, it's not.
It's an argument for hyper-efficiency. It's a deliberate stripping away of the abstraction layers that the tech industry has really relied on for the last decade.
Yeah, and Weaver provides the exact physical baseline he's building this on, which is fascinating.
Yeah, let's establish that. He's using a Debian 13 workstation running the KDE desktop environment, and it's physically wired to a standard Arduino Uno microcontroller.
That specific choice of environment tells us a lot about his methodology before we even look at a single line of code.
How so?
Well, Debian 13 is a Linux distribution renowned for its rigorous stability.
Right.
It's not a bleeding-edge rolling release operating system where software packages update every day and break dependencies. It is rock solid.
So he wants absolute predictability.
Exactly. And pairing that with KDE, which is a highly customizable, somewhat heavy desktop environment, suggests an engineer who demands absolute granular control over their workspace but prioritizes stability underneath.
Okay, that makes sense. And then you have the other end of the wire.
Right, connecting that powerful workstation to an Arduino Uno.
Which is what, an 8-bit microcontroller?
Yes, an 8-bit microcontroller with a 16 megahertz clock speed and a mere 2 kilobytes of SRAM. It creates a massive juxtaposition in computing power.
Phew. 2 kilobytes of memory. You have a modern, multi-core Linux workstation talking to a chip that has less memory than a simple text document.
Yeah, it's wild when you think about it. And Weaver's overarching philosophy is that bridging these two extremes requires a carefully calibrated architecture, not just throwing more code at the problem.
Or a barrage of modern frameworks.
Right. He actually compares achieving this balance to calibrating a warp drive or understanding the balance of the force.
He leans pretty heavily into the science fiction analogies.
He does, but it actually really helps visualize the precision he's aiming for. It frames the engineering problem as a pursuit of elegance.
Okay, let's unpack this. To understand the elegance of the Compass architecture, we have to look at the inefficiency of the systems it's designed to replace.
The bloated ones.
Right. Weaver is highly critical of the historical approach to hardware-to-web interfaces. He actually describes them as a sprawling mess of middleware.
And he's not wrong. Let's examine that sprawling mess.
Yeah, please.
For a long time, the industry standard for getting a sensor reading onto a web page involved a very convoluted chain of command.
Okay.
Developers would typically use a Node.js server.
Because Node is good for web traffic.
Exactly. Node was built for handling asynchronous web traffic and concurrent user connections. But
There's a but.
there's always a but. Node.js was never particularly well suited for low-level hardware communication or complex data parsing. Python has always been the dominant language for data science, instrumentation, and serial communication.
So you have Node for the web, Python for the hardware.
Right. So developers compromised. They built systems that relied on both.
Oh, I see where this is going.
Yeah. A Python script would run in the background, continuously reading the serial port connected to the hardware. But to get that data to the user, the Python script had to pass it to the Node.js server.
So they have to talk to each other.
Yes. This required inter-process communication, or IPC. Engineers would introduce complex messaging libraries like zero-MQ or set up local Redis caches simply to act as a courier between Python and Node.
Wow. The overhead there seems astronomical.
It's basically like needing 3 different translators in a room just to order a coffee.
Right. You're serializing data in Python, sending it over a local socket, deserializing it in Node.js, and then reserializing it again to send over HTTP to a browser.
Precisely. Every single one of those steps requires CPU cycles, memory allocation, and most importantly, time. It introduces massive latency.
And beyond the performance hit, it sounds like a maintenance nightmare.
Oh, it's terrible. You have 2 entirely different runtime environments, the V8 JavaScript engine for Node and the CPython interpreter. You have to manage dependencies for both.
So if one thing breaks,
The whole thing goes down. If the zero-MQ socket drops, the whole pipeline breaks, even if the hardware and the web server are functioning perfectly fine on their own. You're multiplying the points of failure simply to accommodate the limitations of the individual languages.
Weaver's analogy for this is really striking. He compares this old multi-language middleware approach to strapping booster rockets to a perfectly good starship when all you needed was a well-tuned impulse engine.
It's a great analogy. Adding more technology doesn't inherently make a system more capable. It often just increases the drag.
So the Compass architecture, I assume, drops the booster rockets.
It eliminates the Node.js component entirely. Weaver pivots to a unified Python web server.
Just Python.
Just Python. He relies exclusively on it, utilizing the FastAPI framework running on a Unicorn server.
Okay, but wait. If Python was traditionally bad at handling concurrent web traffic, which is why developers use Node.js in the first place, how does a unified Python server suddenly solve the problem without choking under the load?
That's the million-dollar question. The landscape of Python changed dramatically with the introduction of the ASGI standard.
ASGI.
The Asynchronous Server Gateway Interface. That, combined with the maturation of Python's natively built Asyncio library, changed everything.
Okay, break that down for me. What does asynchronous actually mean in this context?
Sure. Historically, Python web servers like Django or Flask were synchronous. They processed one request at a time. If a server had to wait for a database query or hardware read, the entire thread was blocked.
It just sits there waiting.
Right. Node.js bypassed this with its asynchronous event loop. It could go do other things while waiting. But modern Python, specifically frameworks like FastAPI, implements that exact same asynchronous, non-blocking architecture natively now.
Oh, wow. So FastAPI allows Python to send a request to the serial port, yield control back to the event loop, serve 3 other web pages to users, and then pick up the hardware data the moment it becomes available.
You nailed it. It no longer halts the execution of the program while waiting for I/O operations.
That's the mechanical shift right there.
Exactly.
Yeah.
By leveraging FastAPI and Unicorn, Weaver essentially gets the concurrent web performance of Node.js combined with the native hardware interfacing capabilities of Python. He collapses the entire middleware stack into a single cohesive code base.
So there's no zero-MQ.
None.
No local Redis cache.
Nope. The data goes straight from the serial buffer into the web server's memory space.
He describes this unified handling of web traffic and hardware communication as operating with the coordinated precision of a Vulkan logic puzzle.
Another great sci-fi reference.
Yeah. It's this silent, monolithic orchestration. But playing devil's advocate here, there's a counter-argument to this monolithic approach.
Okay. Sure.
For years, the industry trend has been microservices, breaking applications apart so that if the web server crashes, the hardware data logger keeps running. By collapsing this into a single Python application, isn't Weaver introducing a single point of failure?
That is a very valid architectural debate. In a massive, globally distributed enterprise system, like an e-commerce platform, decoupling services is absolutely necessary for scaling.
Right.
But Weaver is designing for instrumentation. He's designing a direct bridge between a specific piece of hardware and a user interface. In this specific context, the network latency and the complexity introduced by microservices far outweigh the benefits.
Because speed is the ultimate goal here.
Exactly. If the goal is sub-millisecond responsiveness from a sensor to a screen, every network hop is a liability.
So it's an intentional rejection of web-scale architecture in favor of embedded systems performance.
Yes. We spent years layering abstractions to make software more flexible, but the cost was always speed. Think about when you tap a smart light switch on your phone and you have to wait 2 seconds for the bulb to actually react.
Oh, I hate that.
Everyone does. You are experiencing the friction of those abstraction layers. Compass is the antidote. It's an aggressive optimization for immediacy.
Okay, so if we fix the server, how exactly is the data physically traveling from the sensor to the screen in real time? Because immediacy requires more than just an efficient backend.
Right. Even if the Python server processes the data instantly, the methodology used to transmit that data from the server to the web browser can introduce artificial latency.
Which moves us into the second major pillar of the Compass blueprint, the communication bridge.
The bridge. Because having a unified backend only solves the server-side processing. You still have the network gap between the Python server and the user's browser.
And Weaver tackles this by explicitly declaring the death of HTTP polling for sensor data.
Yes. HTTP polling has been the default crutch for dynamic web applications for a very long time.
What exactly is polling, for anyone who might not be familiar?
It's like sitting in the backseat of a car on a road trip, repeatedly asking, "Are we there yet?"
Uh-huh.
In a polling architecture, the browser sends an asynchronous HTTP request to the server asking for the latest sensor value. The server responds. A few hundred milliseconds later, the browser opens a new connection and asks again, "Are we there yet?"
That sounds incredibly inefficient.
It's staggering when you look at it at the protocol level. An HTTP request isn't just a simple question, it involves a full TCP handshake. The browser and server have to synchronize and acknowledge each other.
So there's overhead.
Massive overhead. The browser sends HTTP headers, which can be kilobytes of text containing cookies, user agent strings, authorization tokens, all this text just to ask for a sensor reading that might only be 2 bytes of actual data.
It's an incredibly high ratio of overhead to payload.
Exactly. And in the context of continuous sensor data, 90% of those polling requests might return the exact same value if the physical environment hasn't changed. The temperature in the room is still 72 degrees.
So the server is just burning CPU cycles parsing HTTP headers, and the network is congested with redundant requests, all for stagnant data.
Yes. Weaver bypasses this entirely by establishing a WebSocket pipeline.
WebSockets. How does that change the fundamental nature of the connection?
WebSockets, on the other hand, are like a dedicated open telephone line where the driver just says, "We're here," the exact moment it happens.
No more asking, "Are we there yet?"
Right. Instead of the browser repeatedly asking for updates, the initial HTTP request asks to upgrade the connection to a WebSocket. Once the server agrees, the TCP connection remains open indefinitely. It becomes a persistent bidirectional tunnel.
And the moment that tunnel's open, the overhead vanishes.
The overhead is gone. The Python server no longer waits for a request. The moment a new sensor value arrives from the hardware, the server simply pushes it down the open socket. It operates on a push model rather than a pull model.
And Weaver couples this WebSocket pipeline on the front end with the PySerial library on the back end, right?
Yeah.
Communicating over a specific Linux device path.
Yeah.
DevD ACM0.
Yes, the inclusion of that specific device path is a crucial detail in his blueprint. In Linux, everything is treated as a file. DevD ACM0 is the virtual file representing the USB serial connection to the Arduino. PySerial opens this file and reads the incoming stream of bytes.
But wait, this introduces a massive concurrency problem, doesn't it?
Yeah.
One that's deeply technical and often trips up Python developers.
Oh, absolutely.
We established that FastAPI uses Asyncio to handle web traffic without blocking. But PySerial is fundamentally a synchronous blocking library.
Right.
So if you tell PySerial to read a line from the USB port, and the Arduino hasn't sent anything yet, won't PySerial halt the entire thread until data arrives?
Yes, it will.
Yeah.
Which would completely freeze the FastAPI web server. If the thread is blocked waiting for serial data, it cannot respond to incoming WebSocket connections or serve HTTP requests. The Asyncio event loop is paralyzed.
So how does Weaver maintain this, what he calls this beautiful separation of duties without the serial port crashing the web server?
He utilizes OS-level threading in conjunction with Asyncio.
Okay, threading.
Now, Python's global interpreter lock, or GIL, is notorious for preventing true parallel execution of Python bytecode across multiple CPU cores.
Right, the GIL is infamous.
But here's the trick. The GIL is actually released during I/O operations. Weaver exploits this by spawning a dedicated, separate background thread whose sole responsibility is to monitor devd ACM0.
Ah, I see. It's a classic producer-consumer architecture.
Exactly. The background thread acts as the producer. It sits in a permanent loop, blocked by PySerial, waiting for data. But because it's on a separate thread, its blocking nature has zero impact on the main FastAPI event loop.
That is incredibly clever. So
Yeah.
when a line of data arrives from the Arduino, the background thread reads it, decodes it, and then uses thread-safe methods to inject that data into an Asyncio queue that belongs to the main thread.
Yes. The main asynchronous event loop acts as the consumer. It simply monitors the queue, and the moment data appears, it broadcasts it out to all connected WebSockets.
The elegance here is that neither side cares about the timing of the other.
They are completely decoupled in terms of timing. The background thread reads the hardware as fast as the USB port allows, completely unaware of how many web clients are connected. The main event loop broadcasts data to the web clients, completely insulated from the hardware interrupts and serial timing.
What's fascinating here is how removing these micro delays completely changes the user experience from interacting with a machine to experiencing a live feed.
Yes. This architectural pattern, isolating blocking I/O operations into dedicated threads, while utilizing an asynchronous event loop for high concurrency routing, is the gold standard for high-performance data streaming. It guarantees that the system is never waiting on itself.
But a fast connection means nothing if the physical hardware is asleep at the wheel.
True.
We have an unblocked, persistent route from the Python server all the way to the user's screen. But if the physical hardware at the origin point is lagging, the entire pipeline is just efficiently transmitting latency.
Which forces us to look across that devd ACM0 boundary to the actual edge of the network.
Right, let's look at the actual sensor edge. The hardware running the Compass stack is an Arduino Uno executing a C++ sketch designated as Arduino firmware.ino.
And Weaver's philosophy at the microcontroller level is incredibly rigid. He identifies the delay function as the mind killer.
Calling it the mind killer is a brilliant rhetorical device.
It really is.
It's a nod to Frank Herbert's Dune, obviously, where fear is the mind killer. It paralyzes the mind. In embedded systems programming, delay literally paralyzes the processor.
It really does. It's the first function taught in every single microcontroller tutorial out there. If you want to blink an LED, you turn the pin high, invoke delay 1000 to wait 1 second, turn the pin low, and invoke delay 1000 again.
It's incredibly easy to read and understand.
It is. But under the hood, delay is a busy wait loop. It forces the instruction pointer in the CPU to simply count clock cycles until the requested time has elapsed.
So during those million clock cycles, the microcontroller is practically dead to the outside world.
Completely deaf and blind. It's not evaluating if statements. It's not checking the serial buffer for incoming commands.
Using delay is basically like putting on noise-canceling headphones and a blindfold for 5 seconds. You miss everything.
Exactly. If a user clicks a button on the FastAPI dashboard to trigger an actuator, and that command arrives while the Arduino is half a second into a delay function, the command just sits unread in the hardware buffer.
And if the buffer overflows before the delay finishes,
the command is permanently lost.
Wow.
This is utterly unacceptable in an instrumentation environment. Weaver mandates the exclusive use of the millis function to govern timing instead.
Okay, let's translate microcontroller code for the listener. Why does millis solve this? To understand it, we have to look at how microcontrollers handle time without an operating system, right?
Right. The Arduino Uno's ATmega328P chip has hardware timers. These are dedicated silicon registers that increment entirely independently of the main CPU execution.
Oh, independent of the CPU.
Yes. When the Arduino boots, timer 0 begins counting clock cycles. Every time it overflows, it triggers a hardware interrupt that increments a global variable tracking the milliseconds since boot.
So the millis function simply reads that variable.
Exactly. It just checks the time. It does not halt the CPU.
It's like simply glancing at your watch while keeping a conversation going, rather than freezing in place.
That's a perfect way to put it. So instead of writing code that says, turn on the LED and stop the world for 1,000 milliseconds, Weaver's code operates as a state machine.
A state machine.
The main loop runs continuously, thousands of times per second. During each iteration, it checks the serial buffer for incoming commands, and then it checks if millis has advanced past a specific target threshold.
And if the threshold hasn't been met,
It immediately moves on. The loop is entirely non-blocking.
this guarantees a non-blocking main loop. This architecture transforms the microcontroller from a sequential task executor into what Weaver calls a true sentinel.
A true sentinel, always listening, always transmitting. It is simultaneously evaluating the physical sensors and listening for digital commands on every single iteration of the loop.
The real-world stakes of this design choice are massive when you scale beyond a hobbyist blinking an LED.
Oh, the stakes are literally life and death in some applications.
Let's discuss that. What happens when industrial or medical systems use blocking code?
Well, think about an automated manufacturing facility. You have a robotic arm moving at high velocity. It might have a proximity sensor designed to trigger an emergency stop if a human enters the envelope.
Right.
If the microcontroller managing that safety interlock relies on blocking code for routine operations, say, it pauses for just 50 milliseconds to format a data string for a logging server, it creates a 50 millisecond window where the emergency stop is completely ignored.
And at industrial speeds, a 50 millisecond lag can be catastrophic.
It's the difference between a machine shutting down safely or malfunctioning and causing severe injury.
Or in medical devices like a ventilator or an infusion pump, deterministic timing is critical.
Absolutely. The system must process patient biological feedback and adjust mechanical outputs within guaranteed timeframes.
While the Arduino Uno in the Compass stack isn't running a formal real-time operating system, or RTOS, Weaver's strict adherence to non-blocking state machines mimics the deterministic behavior of an RTOS.
It ensures the hardware is never caught sleeping. It creates a system that is continuously vigilant.
So we have the elegant server, the instant WebSocket bridge, and the hyper-vigilant hardware. We have a sentinel, an asynchronous router, and a frictionless bridge. Every layer optimized to remove latency and bloat.
But all of that invisible efficiency culminates at the user interface.
Yeah.
The raw data has to be rendered into visual information.
Right. Now, how does the user actually see all this unseen force? How does Weaver translate the speed of the backend into an interface without reintroducing the exact bloat he spent the entire architecture trying to avoid?
This is perhaps the most contrarian element of the Compass blueprint.
Really?
Yeah. In modern web development, the default assumption is that any interactive dashboard requires a heavy front-end framework. Developers instinctively reach for React, Vue, or Angular and pair them with complex build tools like Webpack or Vite.
Some Weaver.
He rejects all of them. He chooses what he terms the path of the ranger.
The path of the ranger.
He relies entirely on vanilla.js, HTML5, and CSS3.
Okay, for the listener, let's explain what vanilla JavaScript means.
It simply means using the JavaScript programming language in its pure native form without heavy third-party libraries like React or Vue that add overhead.
To appreciate how radical this is in contemporary engineering, we really have to look at the mechanics of a framework like React.
Yeah, React is built by Facebook to solve the problem of rendering massive, deeply nested, constantly changing user interfaces. It does this through a virtual DOM,
A virtual DOM.
document object model. When data changes, React calculates the difference between the virtual DOM and the actual browser DOM and updates only the necessary nodes.
It's an incredibly sophisticated piece of engineering.
It is. But it requires the browser to download hundreds of kilobytes of JavaScript just to bootstrap the framework before it even runs the actual application logic.
And in the context of the Compass stack, that sophistication is actively detrimental.
Exactly. For a simple dashboard consisting of just command toggles and a live data chart, bringing in massive frameworks is total overkill.
A sensor value arriving via WebSocket does not require a complex diffing algorithm to update a single-line graph.
Pushing high-frequency time series data through React state management and virtual DOM introduces computationally heavy overhead that can literally cause the browser to stutter.
So by sticking to vanilla.js, Weaver writes code that the browser executes natively.
Yes. Vanilla.js is exceptionally fast and keeps dependencies incredibly lightweight. There is no translation layer. There's no build step. He doesn't need Webpack to bundle massive dependency trees.
The JavaScript simply listens to the WebSocket and directly manipulates the browser's document object model.
It's the software equivalent of a direct mechanical linkage.
But choosing a minimalist framework doesn't mean accepting a primitive aesthetic.
Not at all. Weaver is highly specific about the visual language of the interface.
Yeah, here's where it gets really interesting, because the look of the software directly reflects the speed and elegance of the backend code. He uses CSS Grid for the layout architecture.
Right. CSS Grid is a native browser specification that completely revolutionized web layout, eliminating the need for heavy CSS frameworks like Bootstrap. It allows for complex, responsive, two-dimensional layouts using a fraction of the code.
And he couples this native layout with a specific design trend, glassmorphism.
Glassmorphism. It relies on CSS properties like backdrop filter to create translucent frosted glass panels over a dark mode background.
And he dynamically fetches the Interfont family from Google Fonts, which is a typeface specifically designed for high legibility on computer screens. The visual aesthetic is highly intentional. He actually states that the interface is designed to evoke a modern LCARS terminal.
Another Star Trek reference.
Haha, yes. LCARS is the Library Computer Access and Retrieval System. It's the iconic, flat-design computer interfaces on the enterprise.
The psychology of this is fascinating. By combining the dark, glassmorphic aesthetic with a library called chart.js for data visualization, he creates an interface that looks fast.
Because chart.js operates on an HTML5 canvas element, right?
Yes. It uses immediate mode graphics rendering. It is incredibly efficient at drawing rapidly updating lines.
Weaver specifically describes the resulting chart.js line graph as buttery smooth. The high-frequency sensor data flowing from the Arduino through the Python async loop across the WebSocket is rendered without a single dropped frame.
The visual fluidity of the front end is a direct manifestation of the architectural rigor of the back end.
However, the path of the Ranger is highly debated in software engineering for a reason, isn't it?
It is. While vanilla JavaScript is indisputably faster and lighter for a scoped project, there is a serious argument regarding maintainability.
Right. If the Compass dashboard eventually needs to scale from a single chart to 50 interconnected data views with complex user state management, vanilla JavaScript can quickly degrade into unmanageable spaghetti code.
Frameworks like React exist to enforce structure on large teams for that very reason.
That's the trade-off. But Weaver's blueprint isn't trying to build Facebook. He's building an instrumentation interface.
And his choice poses a really interesting question. Is the tech world suffering from framework fatigue?
Framework fatigue?
Yeah. Developers are exhausting themselves keeping up with the constant churn of JavaScript libraries, complex build pipelines, and dependency updates. Weaver's blueprint suggests a growing movement back to basics.
Using native web tools to build faster, cleaner interfaces without the massive learning curve and update treadmill of modern web development.
Exactly. It requires a deeper understanding of the browser's native capabilities, but the reward is absolute coherence between the hardware logic and the visual presentation.
Every layer of the Compass stack is aligned toward the same goal.
Pulling all these layers together reveals the true achievement of the Compass stack.
Let's synthesize this journey. From the physical sensors monitored by a vigilant, non-blocking Arduino state machine,
zooming through the USB boundary into a dedicated Python background thread,
processed by an elegant, asynchronous FastAPI event loop,
and a persistent WebSocket pushing that data over the network with zero HTTP overhead.
where a sleek, lightweight vanilla JS client renders it on a hardware-accelerated canvas. It's a masterclass in removing friction.
It's a reminder that in engineering, elegance is rarely found by adding components. It's achieved by ruthlessly eliminating anything that does not directly serve the core function.
So what does this all mean for you? It means that whether you are coding a smart home, managing a lab, or just trying to understand the Internet of Things, less is often more.
Coherence, speed, and simplicity.
But there's a final detail in Weaver's documentation that adds an entirely new dimension to this blueprint.
Yes, the AI element.
Right at the very bottom of his post, a tiny but vital attribution line reads, "This article was developed through conversation with Google Gemini 3 Pro."
Which is an incredibly provocative detail to end on. We have William L. Weaver, an engineer with 30 years of hard-fought experience in physical instrumentation, utilizing one of the most advanced large language models currently available.
The prevailing anxiety in the software industry right now is that AI code generators are going to flood the world with bloated, inefficient software.
Right, because an AI can generate thousands of lines of React and Node.js boilerplate in a matter of seconds. The path of least resistance is simply to accept the generated bloat rather than engineer an elegant solution.
But Weaver's application of Gemini 3 Pro demonstrates the exact opposite.
He did not use the AI to generate a sprawling mess of middleware. He clearly used it as an architectural sounding board.
He leveraged the LLM to refine his own philosophy, to crystallize the Compass architecture down to its most minimal, efficient form.
It suggests that the value of AI in engineering isn't just in its ability to write code faster, but in its capacity to help a seasoned engineer strip away the noise.
In the hands of someone who understands the physical constraints of an 8-bit microcontroller and the protocol overhead of an HTTP request, AI becomes a tool for pure logical distillation.
It acts as an accelerator for the path of the ranger. It allows an expert to quickly prototype and validate native, lower-level implementations that might otherwise be too tedious to write from scratch without a framework.
As AI becomes embedded in the engineering process, will it lead to more bloated code because it's easy to generate? Or will it act like a digital muse, helping veterans like Weaver forge systems that are closer to pure logic?
It's a profound intersection of legacy engineering discipline and cutting-edge artificial intelligence.
Something for you to mull over as we navigate the continuous convergence of the physical and digital worlds. The Compass blueprint stands as a definitive argument for simplicity.
It certainly does.
We leave you with Weaver's own party advice. Keep your loops non-blocking and your variables independent.